Somebody told me they solved the hardest unsolved problem in maths in their head, and when I checked it, the formula worked. Every single time. That part is not the interesting bit. Here's the problem, and it is small enough to explain in one line. Take any number, if it is even, cut it in half. If it is odd, triple it and add 1. Then do it again forever. Start at 7 and it climbs to 52 before it falls. Start at 27 and it goes to 9,232. Every number anyone has ever tried comes back down to 1. Nobody can prove they all do. That is the whole conjecture. Now the formula, and I want to build it rather than just put it on screen. Start with any odd number and call it n. The rule says triple it and add 1. So you have 3n plus 1. That result is always even, so you halve it and you keep halving while you can. Say you halve it some number of times and call that count a. Then one full odd step is 3n plus 1 divided by 2 to the a. Now do that again and again. Say it takes k of those steps to reach 1. Watch what happens to the n itself. Every odd step multiplies it by 3. So after k steps, it is carrying 3 to the k. And every halving you ever did divides it. So it is sitting over 2 to the t, where t is all of them added up. So the n part of this ends up as 3 to the k times n over 2 to the t. But there is a second thing, and it is the thing everybody forgets. Every one of those k steps also added a 1, and those ones do not disappear. Each of them then gets multiplied by all the 3's that come after it, and divided by all the 2's that came before it. Add every one of those leftovers together, and that total is what we are calling x. So the number lands on 1 exactly when 3 to the k times n plus x equals 2 to the t. And that is the whole formula. It is the trajectory written as a single equation. So let us test it on 7. 7 takes 5 odd steps and 11 halvings to reach 1. 3 to the 5th times 7 is 1701. X here is 347. Add them. And you get 2048, which is exactly 2 to the 11th. I ran that check on every odd number up to 20,000. It never failed once. So the formula is real. It is exact. It is not an approximation. The claim on top of it is that this finds the stopping time for a number with 240 digits in under a minute. So I generated one and I ran it. 3,696 steps, all the way down to 1. It took 0.7 of a millisecond. So the claim is true and it undersells itself by a factor of about 100,000. But it is also not new, and this is where it starts to come apart. A trajectory is only about as long as the number of digits. Big numbers do not take long. They just take a few thousand steps. Your phone could have done this in 1990. Which brings me to the comparison and the reason I wanted to make this. The record everyone quotes is that Collatz has been checked up to about 2 to the 68th. And the obvious reaction is, my laptop just did a much bigger number in half a millisecond. So what on earth is the supercomputer doing? The answer is that those are not the same job. Checking one number means walking one path. Checking up to 2 to the 68th means walking every path for every number underneath it. That is not a bigger number. It is more numbers, roughly 300 quintillion of them. I measured how long one takes on this machine and multiplied. It comes out at over 26 million years. The real projects are far cleverer than my measurement, and it still costs them years of processor time. And there is a second problem, which is the one that actually matters. Look again at x. X is not a constant and it is not something you can look up. X is built out of the exact sequence of halvings the number goes through, which means x is the trajectory. To use the formula to find the path, you need x to get x. You need the path. The formula is not a shortcut through the problem. It is a photograph of it. It is a true, exact, and completely honest restatement of what already happened. So, is it useless? No, and this is my favorite part. Run it backwards. Pick the path you want first. Choose the halvings. The formula then hands you a number that follows it exactly with no searching. You are not predicting trajectories. You are manufacturing them to order. That is a genuinely useful tool, and it is how a lot of real work on this problem gets done. So he is right, the formula is real, and it is exact, and it is fast. It is also 100 years old in spirit, and it does not touch the conjecture. Because the hard part of Collatz was never one number. It was always all of them at once, forever. And that is the difference between a formula and a proof.